So we've learned a lot about projectiles that have been launched horizontally, but today we're going to look at projectiles that were launched with an initial velocity that's not horizontal. So let's take a closer look. When our initial velocity is not horizontal, and there's this angle theta, the best way for us to deal with this is to break our vector down into its x component and its y component. And then we can look at motion just in the x direction and motion just in the y direction, just like we've been doing. Alright, so let's start with motion in just the x direction. So the initial velocity in the x direction is just equal to the initial velocity times the cosine of the angle. Acceleration in the x direction equals, what's that? Oh, that's right, the acceleration in the x direction just equals 0. And the only equation we use is our displacement in the x direction is equal to the initial velocity times the cosine of the angle times time. So now let's take a look at motion in the y direction. In the y direction, our football is just going up and it's coming back down. So because it has an initial velocity that has both an x component and a y component, we need to find just the y component of the initial velocity. That way when we look at it in the y direction, our football is just going up and coming straight back down. So how do we find the y component? Well, as we learned before, using trigonometry, our initial velocity in the y is equal to our initial velocity times the sine of the angle. And acceleration in the y direction is equal to what? That's right, negative 9.8 meters per second squared. So if we have the initial velocity, the acceleration, and delta y, which in this particular case, delta y just equals 0, because the football is coming back down to the ground. So now we have all of our givens, and it's just a regular kinematics problem. Let's take a look at an example. So in this example, our initial velocity is 15 meters per second, and our angle is 30 degrees. So in order for us to find out how far the ball went in the x direction, first we need to find out how long it was in the air. So, plugging our values in, we find our initial velocity in the y direction is equal to 15 meters per second times the sine of 30 degrees which is 7.5 meters per second. Our acceleration is equal to negative 9.8 meters per second squared. And our delta y is just 0 because the ball lands back down on the ground. So now that we have our initial conditions in the y direction, we're going to write out our equation and solve for time. So delta y is equal to the initial velocity in the y direction times time plus 1/2 acceleration times time squared. Plugging in our values, we have 0 equals 7.5 meters per second times time minus 4.9 meters per second squared times time squared. Now we're going to rearrange our equation and end up with 4.9 meters per second squared t squared is equal to 7.5 meters per second times time. And now, since we have a t on this side of the equation and a t on this side of the equation, we can divide through by t, and we end up with 4.9 meters per second squared. T is equal to 7.5 meters per second. Divide both sides by 4.9. We end up with T equals 1.53 seconds. Alright, we're almost there. So now we have to look in the x direction, and the velocity in the x direction is equal to the initial velocity times the cosine of the angle. So Vx equals 15 meters per second times the cosine of 30 degrees. So Vx equals approximately 13 meters per second. Acceleration equals 0, and x equals 13 meters per second times our time of 1.53 seconds. So our x equals 19.89 meters. And this is also known as the range. Alright, that's enough for now. Bring in your notes tomorrow.